Good day, engineers. So para sa video natin na to, ang i-discuss natin will be the sample problem for the design of doubly reinforced. So start natin yung discussion para on the problem itself. So kung ano yung state niya. So sabi dito, design the reinforcement of a beam having a concrete compressive strength of 21 megapascal, a steel yield strength of 415 megapascal, a concrete clear cover of 50 mm and diameter 10 mm stirrups are used. The beam carries an ultimate moment from structural analysis which is 320 kN meter, and the cross section is limited to a dimension of 300 mm base and 550 mm height. Use diameter 25 mm bars for compression and tension reinforcement. So, ibig sabihin, limited lang tayo dun sa dimension na 300 by 550. We don't need to change the dimension. We just design it as it is. Then, ang kailangan lang natin i-determine is yung reinforcement niya and yung arrangement ng reinforcement. So, gamitan daw natin ng diameter 25 kung sakaling doubly yung compression and tension, and kung singly diameter 25 mm for the tension bars. So, syempre, list natin yung given. So, binigyan niya tayo ng actual ultimate moment, which is 320 kN meter. Tapos, meron tayong F'C, which is 21 megapascal. Meron tayong Fy, which is 415 megapascal. At meron tayong clear cover na 50 mm. Meron din tayong diameter ng stirrups na 10 mm. So, this is for stirrups. So, first, bago tayo mag-start, kailangan muna natin i-determine yung effective depth at yung D prime natin or yung concrete cover natin on decompression para makuha natin yung raw required. So, to determine that one, syempre, sa design, lagi nating ina-assume na ang dinedesign natin is a single layer reinforcement. So, kapag kukuha tayo ng D, equal na lagi yan sa DT. So, that is equal to 550 minus 50 minus 10 minus 25 over 2. So, ganito lagi yung assumptions sa initial design since hindi natin naman alam pa yung arrangement nung reinforcement unless otherwise stated na i-design natin as two-layered reinforcement. So, that will be equivalent now to a value 955 over 2. This is in mm. Punta naman tayo dun sa compression side. Kunin natin yung concrete cover dun na D prime. So, that will be 50 plus 10 plus 25 over 2. So, that will be a value 145 over 2. So, this is in mm. Ngayon, gamitan natin siya ng Canyetes equation para makuha natin yung required steel ratio niya. So, using the Canyetes equation, for the steel ratio, we could have M is equal to Fy over 0.85 of our F'C. That is equal to a value 415 over 0.85 times 21. So, that will be a value of M equivalent to 8,300 over 357. Next is i-determine natin yung value x. So that will be x is equal to mu over phi bd squared fy. So that will be equivalent to, syempre yung mu natin is 320. I-multiply natin yan ngayon sa 1000 squared para maging Newton mm. Kasi puro mm yung nasa units na nasa ilalim. So, yung phi natin automatically, since we are on the design phase, that is 0.9. Times b, which is 300, times the effective depth kanina na nakuha natin from the previous one, which is 355 or 955 over 2, so that is squared, times the given fy, which is 415. So our value for the x will be equivalent to 0.012525. So ito na ngayon yung value ng x natin. So now we can determine the value of our still ratio. So baba lang natin tong mga figures na to. So for our still ratio, we will have rho is equal to 1 minus square root ng 1 minus 2 mx over m. So para hindi kayo mahirapan, pwede natin i-store to sa m sa calculator and store nyo na to sa x. So para kapag pipindutin na lang natin siya sa calculator, ang gagawin na lang natin is 1 minus 2 alpha m alpha x over m. So using our calculators, we could get a value of rho required, which is 0.015217. So ito na ngayon yung still ratio required natin by using the Cañetes equation. You can use any equations you want for the still ratio. Meron naman tayong tatlong types ng equation na pwedeng gamitin. So now after getting our still ratio, syempre kunin natin yung maximum still ratio. So for our maximum still ratio, syempre kakailanganan natin itong diagram na to. So kunin natin siya. So we have to check rho max. So, coming from this diagram, syempre, ito siya. So, pwede nga natin i-shift pababa yun. So, i-derive na lang natin yung equation ulit. Pero, although na-derive na natin siya from our previous videos, so, that will be syempre, similar triangle, 0.003 over C max for our upper triangle, which is ito. Then, yung isa pang triangle natin, yung mas malaki, which is itong triangle na to. Ayan. So, shade ko na din. Ito siya. So, ayan, triangle na yan. So, that will corresponds to equal to 0.003 plus 0.005 divided by dt. And as you can see, we can rearrange this equation para makuha natin si C max. So, that will be C max is equal to a value that is 0.003 divided by 0.003 plus 0.005 d sub t. And simplifying this equation, we could get 3/8 of dt. So, ito na ngayon yung value ng C max natin. Then, we can get the value of the rho maximum. Kunin lang natin to from this stress diagram. So, alam natin na this will corresponds to a maximum still ratio for singly kasi ang gamit nating diagram is for a singly reinforced. So that will be C is equal to T. So that is 0.85. F prime C. So that will correspond to A max B is equal to AS max Fy. We already know that A max is equal to beta 1 C max and AS max is equal to rho max BD. So substituting these values to our equation, we could get 0.85 F prime C beta 1 C max B is equal to rho max BD Fy. And we could cancel this one, yung B. Then, we could substitute the value of C max, which is 3/8 of dt. So, that will be 0.85 F prime C beta 1 times 3/8 of dt is equal now to rho max d Fy. Then, arranging the term to get the equation for our rho maximum, we could have rho max, which is 3/8 times 0.85 F prime C beta 1 over the Fy times dt over the d. So, ito na ngayon yung value ng maximum still ratio natin, and we could substitute the values or the magnitude. So, that will be equivalent to 3/8 times 0.85 times 21, and yung beta 1 natin is 0.85 pa rin kasi yung F prime C natin is that is less than 28 divided by our Fy is 415. So, etong term na to sa equation natin will be cancelled out. Itong term na to. So, that will just be this equation. So, coming from this equation, we could have rho maximum is equal to 0.01371. And as you can see, if we compare this one to our required still ratio, yung na-compute natin kanina, which is ito, so mas malaki si required still ratio compared kay maximum still ratio. So, this is less than rho required. Therefore, design a doubly reinforced beam. So, wala naman tayong ibang pwedeng magawa kasi limited tayo sa dimension na 300 mm by 550 mm. Pero kung hindi tayo limited, we can change the dimension and ipasok natin siya sa part ng singly. Pero since hindi tayo pwedeng mag-change ng dimension, we have to design it as doubly reinforced beam. So, to design a doubly reinforced beam, so sunod na dito is to determine AS1 by using the rho maximum as its still ratio. So, AS1 will just be equivalent to rho max BD. Sabi ko nga kanina, rho max yung ginagamit natin kasi the first stress diagram, which is shown dito. So, etong stress diagram na to, is for a singly reinforced. And we take a value na kapag rho required is lesser than or equal to rho max, nandun kasi yung part na equal. So, ibig sabihin, we take it as singly. And yung first diagram or first stress diagram ng ating doubly reinforced beam is corresponding to a singly reinforced. So, valid yung paggamit natin ng maximum steel ratio for the first steel area. So, substituting the value of rho max, so that will be 0.013 71 times 300 times 955 over 2. So, calculating that one, we could get AS sub 1 equivalent to 1963.9575. So, this is in mm squared. Now, we can proceed in determining the depth of compression block, yung theoretical sa design natin, and yung the depth of the neutral axis. So, syempre, dun sa pagkuha nun, gagamitin natin yung first stress diagram, which is ito. So, we will be needing its equilibrium equation, which is C1 is equal to T1. So, using C1, lagay na lang natin siya on the right side, on the left side. So, that is C1 is equal to T1. Now, we can have, so, ito naman yun, yung C1. So, that is 0.85 F prime C AB is equal to, syempre pwede na natin gamitin yung AS1 kasi nakuha na natin yan. And since this is the sign, we will use FY. So that is 0.85 F prime C AB is equal to AS1 FY. Then arranging the term, we could get A is equal to AS1 FY over the 0.85 F prime CB. So we have to substitute the values on this side. So that will be 1963.9575 times 415 divided by the value 0.85 times 21 times 300. So that will be a value of the depth of compression block equivalent to 152.2021 mm. After getting this depth of compression block, we can proceed in getting the value of the depth of the neutral axis or the distance from the extreme compression fiber to the zero strain, which is the value C. So that will be coming from A is equal to beta 1C, or the value C is equal to A over our beta 1. So substituting the values, we have 152.2021 divided by beta 1 natin is 0.85 kasi less than 28 yung ating F prime C. So the value of C now coming from this calculation will be 179.0613. So this is in mm. So ngayon meron na tayong depth of compression block and the depth of the extreme compression fiber to the zero strain. Now from the same stress diagram, we could get the nominal, the first nominal moment. So from this diagram, pwede natin kunin yung first nominal moment since meron na tayong A value or the depth of compression block value. So that will be pwede natin kunin siya on the tension side or pwede rin yung sa compression side. So for this problem, kunin natin siya on the tension side. So that will be Mn1 is equal to AS1 Fy times D minus A over 2. So we have to substitute our values. So AS1 will be 1963.9575 times Fy is 415. So multiplied by D, yung kanina natin na nakuha, which is 955 over 2, minus yung A natin, which is ito na 152.2021. That's 152.2021 divided by 2. So multiply natin to by 1 over 1,000 squared. So the first nominal moment coming from this one will be equivalent to 327.1571. So that is in kilonewton meter. So yan ngayon yung ating first nominal moment na pwede natin magamit for the design process. So syempre, after getting yung first nominal moment natin, we can now proceed dun sa pagkuha ng steel stress natin para makita natin kung yielding yung compression steel or hindi. So mangyayari lang yun kung gagamitin natin yung strain diagram. Hindi ko na siya i-derive. So we just proceed dun sa derived equation, which will be F prime S is equal to 600 times C minus D prime over the value C. So substituting the value, so dito tayo. So that will be equivalent to 600 times 179.0613 minus our D prime, which is 145 over 2, divided by our C ulit, which is 179.0613. So calculating this value, we could have F prime S equivalent to 357.0664 megapascals, and this is actually lesser than our yield strength for our compression bar. So therefore our steel does not yield, and we have to use the F prime S as a value for our next calculation. After determining if our compression steel is yielding or not, so proceed tayo on the part of getting the second nominal moment. The second nominal moment is coming from, kunin ulit natin yung diagram na to. So coming from this diagram, manggagaling siya on the second stress diagram. So dito. So syempre that will correspond to Mn2. Pero since meron tayong Mn1 na given kanina, and we all know that yung Mu natin is given, and meron din tayong Mn1 na nakuha kanina. So that will be Mn natin is equal to a value Mn1 plus Mn2. Ang required natin will be Mn2. So our Mn2 is equivalent to a value Mu over Phi minus Mn1. So ito kasing part na to is also the Mn or the nominal moment. So, calculating this one, we could get Mn2 equivalent to 320 divided by yung phi natin which is 0.9 minus Mn1 na calculated natin kanina which is 327.1571. So, we could have a value 28.3985. So, this is in kilonewton meter. Ito na ngayon yung ating Mn sub 2. Ngayon, after getting that second nominal moment, pwede na ngayon tayong kumuha nung AS2 gamit yung sinasabi kong diagram na to. So, we will just sum up moments dun sa part ng compression side. So, kunin natin yung moment on the compression side. So, that will be Mn2 is now equal to AS2 Fy times D minus D prime. And we are to arrange this term, we could get AS2 as Mn2 over Fy times D minus D prime. So, our Mn2 is 0.3985. This 28.3985 times 1,000 squared. So, para maging Newton mm divided by 415 times 955 over 2 minus 145 over 2. So, yung hinahanap natin na value ni AS2 will just be equivalent to 168.9633. That is 168.9633 mm squared. Yan na ngayon yung second steel area natin. Now, pwede na natin makuha yung total tension steel area. So, our total tension steel area will just be AS is equal to AS1 plus our AS2. So, that will be AS natin or AS1 natin is yung 1963.9575 kanina. I-add natin sa 168.9633. So, we could have an AS equivalent to 2,132.9208. That is in mm squared. Ito ngayon yung tension steel area natin coming from the design. Now, hindi pa tayo tapos kasi we have to determine yung compression steel area since this is a doubly reinforced beam. So, makukuha natin yon by using the equilibrium equation for this diagram. So, yung second diagram natin. So, that is C2. So, that will be C2 is equal to T2. So, for that instance, we have A prime S for our compression side. That is A prime S. Ngayon, ang gagamitin natin, since na-prove natin kanina dito na kailangan natin gamitin yung F prime S kasi the compression steel is not yielding. So, that should be F prime S minus 0.85 of our F prime C is equal to AS2 Fy. Then, rearranging the term. So, that is A prime S is equal to AS2 Fy over F prime S minus 0.85 of our F prime C. So, that will be a value 168.9633. Yung kaninang nakuha natin, times 415 divided by the F prime S, which is 357.0664 minus 0.85 times 21. So, that will be A prime S is equivalent to a value 206.711 mm squared. Ngayon, meron na tayong compression, steel area, and nakuha na din natin yung tension steel area. After getting those two, we can proceed to determining the number of bars. So, doon na tayo sa number of bars. Simula tayo on the part of the tension area. So, N is equal to the AS over the area bar. Sabi, we have to use diameter 25 mm bars. So, we have an AS computed kanina, which is ito. That is 2132.9208 divided by pi over 4 times 25 squared. And that will be a value equivalent to 4.3452. And approximately that is 5 pieces. Then for our next one, we have to determine the number of compression bars. So that will be N prime is equal to A prime S over the area of the bar. So that will be 206.711 divided by pi over 4 times 25 squared. So approximately ang lalabas dito is 0.4211. So at times may magsasabi na that is 1 piece. Kasi nga, hindi naman siya nag 1 point something. Kaya hindi natin pwedeng sabihin na 2 pieces. But according to the code, the minimum number of bars should be 2. Kasi dalawa yung lagi nating ine-extend dyan. Dalawa yung continuous dyan. So, that will be approximately 2 pieces. Hindi kasi pwedeng 1 piece lang yan ng diameter 25. So now we have 5 pieces of diameter 25 and 2 pieces of diameter 25 for compression. Yung 5 pieces is for tension. Now, to determine its arrangement, we have to check the spacing requirements. So let's check spacing. So let's say single layer yung single layer for tension. So kapag chinek natin single layer yung tension, so RS will be equivalent to B minus dalawang concrete clear cover minus 6 na diameter ng stirrups minus N minus 1 times diameter ng bar divided by N minus 1. So, that will be equivalent to 300 minus 250 minus 6 na 10 minus 5 minus 1 times 25 divided by 5 minus 1. Our spacing for this instance will be equivalent to 10 mm. And this is much lesser than 25 mm requirement. Kasi we assume na ang diameter ng aggregates dito is 3/4. Pero kung hindi man, kung 1 inch yan, 25 mm pa rin naman yun. So, we have to try through 2 layers. So, trying 2 layers, we could have tatlong diameter 25 sa first layer at dalawang diameter 25 sa second layer. So, automatically, ang kunin na lang natin kung papasok sa spacing is yung tatlong diameter 25. Kasi, kung pumasok man sa spacing yung tatlong diameter 25, papasok na yung dalawang diameter 25. So, to check, that is S is equal to 300 minus 250 minus 6 na 10 minus 3 minus 1 na 25 divided by 3 minus 1. So, that will be a value equivalent to 45 mm. And this is greater than our value 25 mm. Therefore, okay yung spacing na yun. Next, yung side naman ng compression, since dalawang bars lang yun, and pumasok sa spacing yung tatlong diameter 25, so hindi na natin i-check kasi alam na natin na papasok din naman yon sa spacing. So, kung pinapahanap lang, so kunin na din natin S prime is equal to 300 minus 250 minus 6 na 10 minus 2 minus 1 times 25 divided by 2 minus 1. So, that will be a value 115 over 2. Approximately, that is 57.5 mm. And that is greater than our value or our minimum, which is 25 mm. And that is okay. So, ang magiging design na nung ating beam is ito. Pero, hindi pa natin siya pwedeng sabihin na siya na yung design. Kasi nga kailangan natin i-double check yung capacity nitong beam na to. Kung papasok siya dun sa actual, yung actual capacity niya is papasok dun sa actual ultimate moment. So, putulin muna natin yung discussion on the sample problem and we will discuss the analysis of this design beam on our next video. So, this is all for the design process nitong doubly reinforced beam, and for the analysis part, this will be discussed on our next video. So, just a reminder, hindi pa siya pasado as the design of this beam. So again, this is Engineer Rodolfo. Thank you for watching and don't forget to subscribe to Butch TV.